Hello, and welcome to the series where I take a game that I started in high school and try to improve it using the knowledge that I've gained in the years since I started writing it. In the last video, we talked about stack blasting, and we used it in kind of the easiest possible case where you take a solid pattern that you can just encapsulate in 8 bytes and then just repeatedly blast it into the screen buffer. Today, we're going to take it one step further, so I strongly recommend that you watch that video first so you get your bearings and get the idea of how stack blasting works. Because today we're going to talk about 2 stack pointers at once, and we're going to talk about the things you've got to do to get your buffer ready to be sucked in and blasted by the registers. It is quite complex. So you could say we're going to kick it up a notch and start cooking with fire. Are you ready for this jelly? Well then, buckle up, because it's gonna be... So here's the problem. We want to blast this onto the screen. So the question is, what do we put in our buffer so that we can pull the bytes from our buffer into the registers and push those registers onto the screen and have it look like this? From the last video, you know the answer can't just be this. Instead, we have to turn it upside down so that as we read from the beginning of the buffer, we can write those bytes to the end of the region of the screen where the mountains need to be displayed. So we can do pulls up here and pushes down here, and everything gets written in the right order. Except there is a problem with this. So to help visualize this better, let's number our bytes. So now imagine this is what we're trying to put on the screen, and each of the numbers represents a byte value. So it's like our pattern is so simple, we're just doing byte 0, and then byte 1, and then byte 2, and then byte 3, and so on. And you'll see we have hex 20 bytes per line, just like we normally do on the screen. So as I mentioned before, whatever you keep in the buffer can't simply be the upside down version of this. But why? To understand better, let's take a look at what happens in the debugger. Here's the code we're going to step through. We're going to do 2 pairs of pulls and pushes. So we're going to start by pulling wherever S is pointing, which is the beginning of our source buffer, these 8 bytes. And then we're going to push those 8 bytes wherever U is pointing, which is hex 10 bytes into the beginning of the screen buffer. So we'll start at E10 and we'll keep pushing to smaller and smaller addresses until we hit the beginning of the screen buffer at E00. So you'll notice I'm doing things a little bit differently than in the last video. First of all, I'm using 2 stack pointers because the 6809 gives us 2 stack pointers. And I'm no longer blasting the same byte over and over and over and over again. So this way I can reserve S to point to the buffer I'm reading from, and I pull from that. And I can reserve U to point to the screen buffer that I'm writing to, and I can keep on pushing to that. So this pair will blast the first 8 bytes, and this pair will blast the next 8 bytes. The other thing I'm doing differently is I'm using the DP and the CC registers as the registers I'm pulling and pushing to and from. I've got to do that to continue doing 8 bytes at a time because I can't use U anymore as one of the data registers since I'm reserving it as one of my stack pointers. There are caveats with using DP and CC in this way, and I will talk more about that later, but for now it's not an issue, so don't worry about it just yet. And this simulates our source buffer, and just like in the visualization from before, we're starting at 7F and going backward until we get to 7.0. And the hope is that when we push those into the screen buffer, we'll get 7.0 through 7F in order. So here we are in the debugger, and up here we have our source buffer, and we're starting at 7F, and we're going down to 7-0 like we expect. And down here is our screen buffer, which starts at E100. The pushes should start here at the end and work their way toward the beginning. So the first thing we're going to do is to pull from S into these registers. S is at 3F19, and 3F19 you can see has our buffer going from S7F down to 7.8, which will read into these registers. And sure enough, if we take a look, CC is 7F, D is 7E, 7D, DP, 7C, and X and Y are 7B, 7A, 79, 78. Perfecto! What could possibly go wrong? And now we're going to push those registers to wherever U is pointing, and U is happily pointing at E10. And if we look here, well, it's going backward. It's going backward from 7F to... Shouldn't we have 7F here, and then we would be going backward to 7.8? Right? That was the whole point of positioning U at the end. We would start here, and then we would go backward with the backward numbers. But we went backward with the other way. What if we start pulling from 7F going to 7.8? Shouldn't we then start pushing from 7F going to 7.8? What? Nope. Let's do another pair and see if that clarifies it. We're going to pull from S, which is now happily at 3F21, which is right here. So we should see 77 through 70 going into those registers. And sure enough, we've got 77, 76, 75, 74, 73, 72, 71, 70. And perfect, let's push them wherever U is, which is E08, right here. Let's push. What a mess! What a mess! Instead of it starting at 70 over here, and then going all the way up to 7F, no, it starts at 77, goes down to 70, then jumps back up to 7F, and then goes down to 78. It might not be what we want, but it is exactly what's supposed to happen. And the reason is that push and pull will push and pull registers in a predetermined order. It does not matter what order you specify here. Now, it just so happens that I did specify them in the actual order they'll be pushed and pulled. So if we took a closer look, then it would make sense what's going on. Most 6809 references will actually tell you what the order is that registers are pushed and pulled. So if you push, then registers will get pushed in this order. And if you pull, they will get pulled in this order. So let's tell the debugger to rewind a bit. We already carefully verified that each of these registers are pulled in this order because we saw that CC was the biggest byte, 7F, which is the first byte right here. And then it kept going down, 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 down. 7F down to 7.8. So what is getting pushed? Well, first we're going to push Y, and we're pointing here at the end. So at the end, we're going to push whatever Y has, but not just that. First, we're going to push the low byte of Y, and then we're going to push the high byte of Y. So we're going to push 7.8 and then 7.9, boop, boop, and then we're going to push X, and again low first, so it's going to be 7.8, 7.9, 7A, 7B. And so if we just move forward again, then we'll see it did exactly what it promised it would do, 7.8 up through 7F. So the way to internalize this is that each individual push and pull pair will not change the order of the bytes. So if the bytes were reversed to begin with, they're going to stay reversed over here. But from one push-pull pair to the next, you will see the opposite ordering from what you have in the buffer. So if you think of them as groups of 8, you can call them octets. The very last octet on the screen was the very first octet from your buffer. The next to last octet on the screen will be the second octet in the buffer. And that's what we expect. But within the octet, the order remains the same, which you can see after I've done the second push-pull pair. The order within the octet is descending, 77 through 70, just like it was descending in the original buffer, 77 to 70. So it's not enough that we have our buffer store everything upside down. We do, but within each octet, they have to be unreversed. So let's make that adjustment to the code. So now our last octet comes first, just as before. The last octet came first before. But the difference now is that within the octet, we want the bytes in order. And then the next to the last octet comes next, just as it did before. But again, the difference is the bytes within the octet go in order. So let's see if the debugger agrees with me. So now you can see the source buffer is doing that upside down, partially unreversed nonsense. The last octet comes first, but the bytes within it ascend. The next to last octet comes next, and those bytes ascend. So let's do the first pair of pulls and pushes. And here we have our last octet, and it is descending as I go to the left, like I wanted, or ascending as you go from left to right. Let's do the second pair. And look at that. All of our bytes in order from 7.0 to 7F, just as we wanted. So we just have to do this with the whole freaking picture. Once again, we have our buffer at the top and the screen we're trying to produce at the bottom. And as before, the buffer is in reversed order. But this time we're doing it in groups of 8. So the very first byte is not at the very end, it's actually over here. So we would go from 0 to 7, and then from 8 to 0F, and then 10 to 17, 18 to 1F, and so on. So that's how we need to order our buffer so that it's ready for stack blasting. So what does this look like? Well, this is what we want on the screen. This is what the buffer would look like if we just made it upside down. But this is what it looks like when we unreverse the octets. So we're done, right? As long as I organize my buffer like this, I can stack blast it and everything should work fine. Well, not quite. Recall that I'm not just trying to draw a static pictures of mountains on the screen. I'm trying to scroll them. So how did I scroll them before? In my buffer, I would just store the mountains normally, forwards, and I would keep track of where I was in the scrolling by using this kind of cursor. This is like a rotational offset that tells me where I'm starting. So to draw the mountains on the screen, I would start here and I would just go to the end. And then I would resume at the very beginning and go up to the cursor. But in this case, the cursor is at the left, so there is no second spot. And then for the next frame, I'd move the cursor forward. And so again, I start drawing from the cursor to the end. And then for the remaining portion, I start at the beginning and go up to the cursor. And then I would just keep doing this. Move the cursor around, left half, right half, left half, right half, left half, right half. Life was so simple back then. And then you do it fast enough and it gives that simulation of moving. So to make this work with stack blasting, first of all, the buffer has to store our data upside down and partially unreversed like before. But now the rotational offset needs to be at different places than it normally would be. It doesn't start at the beginning and just go across. It starts at the last octet, but at the beginning of the last octet. So it actually starts here, and then it continues to go forward through the octet. And then once it's done, it goes to the previous octet, but again starting at the beginning, and it goes through that. And then the previous one and previous one. And then when it reaches there, it wraps back around. That also means that the code that's going to blast the resulting bytes onto the screen have to cut things up in quite a different way. So we start wherever the cursor is, and then we go to the right, and then we go to the previous octet, and we do that all the way to the right. And that covers the first half. The second half would then start at the last octet, which is the first octet, starting here, going across, here, going across, and then finally the octet our cursor is in at the beginning and then going across to it. And that leaves all sorts of fun cases, like what if your cursor is at the very beginning of an octet, or at the first octet or the last octet? How many octets can you just blast directly, and how many do you have to do partially? Took a while to get everything just right. Finally, let's talk about the caveats with using the direct page and the condition code registers as part of your stack blasting. I don't really have enough time to go into detail about what DP does, but the very quick summary is when you're referencing an address, the CPU has a built-in way to reference that address quicker and with fewer bytes by using the DP register as the high byte, and then whatever the assembler wrote into that instruction would be the low byte. You can actually change the DP register to wherever you want in memory. If, say, you have a bunch of variables stored in a certain location, you can move DP over there, and then all those references will be faster and smaller. But while you're using it during stack blasting, you're changing it. And so if there are any direct addressing instructions during that stack blasting session, the CPU is going to use what's in DP, even though it's pretty much garbage. Now, by default, DP is just 0, so unless you have any code that references an address whose high byte is 0, it's actually not going to be a problem. But if you call any ROM routines, there are variables up in the 0 area, and so it will be referencing those, and so you've got to be super careful. One thing you can do is to give the assembler a hint that the contents of the DP register are something that none of your addresses are going to use anyway. So for example, if you promise you're never going to access an address whose high byte is 80, you just set DP to 80 using this hint pseudo opcode, and then the assembler will refuse to use direct addressing mode since it won't be seeing any addresses whose high byte is 80. Just be careful what you put here to be something you promise you're never going to be referencing during stack blasting. And of course, you can set and unset this around the stack blasting code. Finally, the condition code register has the stuff you would expect, like the result of compares and tests. So obviously you're not going to rely on this in a conditional branch right after you do stack blasting, because the contents will be overwritten by that stack blasting. But it also has bits that are related to interrupts. So this is yet another reason to make sure you disable interrupts around stack blasting. And in the previous video, I talked a little bit more about the caveats of interrupts. Well, it took some doing to get stack blasting to work with scrolling regions, but that's not the only thing that I did in the code that you saw running. I also used self-modifying code to improve the efficiency of certain places. So in the next video, we're going to explore why on earth I did that. So I will see you next time.